Okay, we are talking about fields and forces, electric fields and electric forces and the relationships. So let's just start with a straightforward problem. Let's say that we're in a constant field. So far we've been talking about fields due to point charges, and we've been summing up fields due to point charges. And we have to sum up the vectors and take components, and we know that the net electric field is equal to the individual electric fields, E1 plus E2, of all the point charges that make up a system. But let's say that we've got a more complicated system, right? And so we've got a constant field. And one of the questions is how do you get a constant field? Right? A point charge does not have a constant field, right? A point charge has a field which goes as kq over r squared. That's not a constant field. It changes with distance. It changes with r. A constant field, so a point charge field looks like this. All right, it changes. It gets smaller as you get farther away from the charge, which is, I was assuming there's a plus charge in the center. A constant field looks like this. So the lines don't get any farther apart. And a constant field actually comes from a large or infinite sheet of charge. So a large or infinite sheet of charge. That's how we get constant fields. And if you imagine putting together a whole bunch of point charges, but you put them together in a two-dimensional sheet, then all of the components which are parallel to the sheet are going to cancel, and all the components which are perpendicular to the sheet are going to add, and you're going to get a constant field. We're going to show that. But before I get there, let's do a problem with a constant field. Let's say that we have a constant field of 60 newtons per coulomb. And let's say that an electron is put in that constant field. What does the motion of the electron look like? Blue dot is my electron. And what does the motion of the electron look like? Well, the electron is going to feel an electric force. What kind of electric force is it going to feel? It's going to feel an electric force. The force on the electron, so the force on the electron, I'm not going to write the words, is equal to the charge of the electron times the field that it's in. So the electron is going to feel a force which is equal to, the charge of the electron minus 1.6, times 10 to the minus 19 coulombs, look up the charge of an electron, times the electric field, which is a constant 60 newtons per coulomb. So no matter where the electron is in the field, because it's a constant field, whether the electron is over here or over here or over here, no matter where it is, it's going to feel a constant electric field of 60 newtons per coulomb. And so it's going to feel a force of minus 60 times 1.6 is 96. 96 times 10 to the minus 19th newtons, coulombs times newtons per coulomb. What does the minus sign mean? Well, the minus sign indicates here that it's going to feel it in the opposite direction of the plus direction, which was the direction of the field. So the direction of the field, or it's just minus, it's the opposite of the direction of the field. Opposite the direction of the field. So the electron is going to feel a force, I was drawing in blue, but it's going to feel a force in this direction. It's going to feel a force opposite the field. Remember the definition of the direction of a field line. The direction of a field line is the direction of a force on a positively charged particle. So therefore, a negatively charged particle feels a force in the opposite direction. That's what the minus sign indicates here. It indicates that the direction of the force is negative of whatever the positive direction was. And I guess we were just assuming this is the positive direction, the direction of the field. So it's minus 96 times 10 to the minus 19th newtons. And as the electron moves to the left, when it gets over here, what's the force the electron feels? It's still minus 96 times 10 to the minus 19th newtons because it's a constant field. Because it's a constant field. So what is the motion of the electron? It's a constant force. So it's a constant acceleration. So the electron is accelerating at a constant rate. Actually, why don't we just figure that out? If this is the electric force on the electron. If we ignore gravity, if we assume that this is the only force on the electron, so we can just say, this is equal to F equals this net force equals ma. And if the net force So now we can say, okay, this is the positive x direction. The net force is in the minus x direction. Minus 96 times 10 to the minus 19th newtons in the positive x direction equals the mass times the acceleration. So remember, the question I asked is what kind of motion, or what happens to the electron? What kind of motion does it undergo? It undergoes constant acceleration motion. I'm going to show you that. We just wrote down F net equals ma for the electron. The net force is the electric force. So we plug in the electric force, and we set it equal to ma. What m is this? We're talking about the net force on the electron, so it's the mass of an electron. So you ask, hey Alexa, what is the mass of an electron?
An electron's mass is 0.00055 unified atomic mass units.
Oh boy, that wasn't very useful. Hey Alexa, what is the mass of an electron in kilograms?
An electron weighs 9.109 times 10 to the power of minus 31 kilograms.
There we go. So Alexa says it's 9.1 times 10 to the minus 31 kilograms. And so we can go ahead and plug in the mass of the electron to find the acceleration of the electron. Therefore, the acceleration of the electron is, again, if now I'm taking into account the directions, it's minus 96, not 9.6. Let me go ahead and just write this on a new page. Sorry about the mess. Okay, therefore, right, we had F net, I'm just going to rewrite some of this, ma minus 96 times 10 to the minus 19th newtons, x direction, is equal to the mass of the electron, 9.1 times 10 to the minus 31 kilograms times the acceleration of the electron. Therefore, we solve for the acceleration of the electron, not triple equals, but the acceleration of the electron. We divide both sides by the mass. And if I did the math correctly, I get 1.05 times 10 to the 13th meters per second squared in the minus, the minus sign, in the x direction. So it's in the negative x direction. It's 1.05 times 10 to the 13th meters per second squared. Is that a large acceleration? Yes. Yeah, it's an extremely large acceleration. You couldn't accelerate, right? The human body can't accelerate faster than about, 10 Gs or 100 Gs without injury or death. And 100 Gs is 980 meters per second squared. This is a billion times bigger than that, or 10 billion times bigger than that. But it's an electron. It can handle it. It's a point particle. So the motion of the electron is it goes opposite the electric field with a constant acceleration of 1.05 times 10 to the 13th meters per second squared. That's the magnitude of the acceleration.